Hello, today we are looking first at 2.7, which is finding square roots and comparing real numbers. So first, we're going to list all the perfect squares from 1 to 225. We're really not going to 225, we're really going to 15 because 15 times 15 is 225. So, we call these our perfect squares because we know both sides, all sides of a square are equal. So if I were to tell you 3 times 3, well, 3 times 3 is 9. That's the same as saying 3 to the power of 2 equals 9, because it's 3 2 times. So we're going to start with 1, because we could have 1 times 1 equals 1. So 1 squared equals 1. Then we're going to go 2. 2 times 2, or 2 squared, equals 4. Then 3 times 3, or 3 squared, equals 9. 4 times 4, or 4 squared, is 16. Then 5 times 5, or 5 squared, is 25. 6 times 6, or 6 squared, is 36. 7 times 7, or 7 squared, is 49. 8 times 8, or 8 squared, 64. 9 times 9, or 9 squared, equals 81. 10 times 10, 10 times 10 is going to give us 100. 11 squared, or 11 times 11, is actually 121. 12 times 12, or 12 squared, is 144. 13 times 13, or 13 squared, this one's a little tricky, it's 169. 14 times 14 is going to give us 196. These ones get a little bit tricky down here. And last, 15 squared, or 15 times 15, is 225. So these are what are called our perfect squares, because 2 of the same number would make a square. 2 times 2 is 4, 3 times 3 is 9, and so on. We can also go the opposite way. The opposite of some number squared is taking the square root of that number. So if I was to take the square root of 4, what number multiplied by itself gives us 4? Well, 2 times 2 is 4, so the square root of 4 is 2. Same thing with 9. If I was to take the square root of 9, well, what number multiplied by itself gives us 9? Well, 3 times 3 is 9. Same with the square root of 16. Square root of 16 is 4 because 4 times 4 is 16. We could go on. Square root of 25 would be 5. Square root of 36 would be 6. Square root of 49 would be 7. We could list all of these. Square root of 1 equals 1. All the way across. I'm not going to because you can see that, hopefully you know when we get down here, the square root of 225 is going to equal 15. So we're going to be looking at these numbers. All of our perfect squares are what we call rational numbers because they make sense. They're nice whole numbers. They don't have any decimals. So like I just said, here are our rational numbers, some of our rational numbers, like the square root of 4 because it's really just 2. On the other hand, we have irrational numbers. These are numbers like pi that go on and on forever. 3.14159, ... Okay? These irrational numbers, they don't repeat. Nothing pi, or they doesn't repeat. Or every square root that's not a perfect square, like the square root of 18, would be somewhere between 4 and 5, because square root of 18 is not a nice number. There's not a number that multiplies by itself to give you 18. So it's somewhere between 4 and 5. It would be like 4.2, ... It would go on and on. Same thing with 70. The square root of 70 is not on here. Those are irrational numbers or crazy numbers. So let's do a little bit of simplifying first. Evaluate these rational numbers that make sense. What does this mean? It just means we have the positive and the negative answer. That's what they're looking for. So the square root of 36 is just 6. So they're looking for a positive 6 and a negative 6. The square root of 49 on our list right there is 7. So that's 7. The square root of 121, way down here, is just 11. Square root of 16, hopefully you should know 4 times 4 is 16. And 100, square root of 100 is really just 10. And then our last one here, we know our answer is going to be negative because there's a negative sign. What number multiplied by itself gives us 4? Well, the answer should be 2. Moving on to the other side, now we're going to look at some irrational numbers, some numbers that are not nice. We are looking between which two consecutive integers or consecutive numbers is the number located. So 37. If we look at our list here, the square root of 37 is not on our list. It's between the square root of 36 and the square root of 49. So I'm going to write that it's between the square root of 36 and the square root of 49. Well, if we simplify, the square root of 36 is really just 6, and the square root of 49 is really just 7. So if I were to plug this in your calculator, it would be somewhere between 6 and 7. Like 6.12, blah, 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 on and on. Square root of 50 is our next problem. Square root of 50 would be really close to 49. It's a little bit bigger though, so it's between 49 and 64. So it's between the square root of 49 and the square root of 64. Well, 7 times 7 is 49, and 8 times 8 is 64. So our answer would be between 7 and 8 if we were to plug that in our calculator. 103 is our next one. So 103 was between 100 and 121. So it's between the square root of 100 and the square root of 121. The square root of 100 is 10. And then the next number would obviously be 11. The square root of 121 is 11. So your answer would be somewhere between 10 and 11. So let's find the square root of 11, our next one. 11 is between 9 and 16. The square root of 9, square root of 16. And both these numbers are negatives as well. So this is really, the square root of 9 is 3, so negative 3. And the square root of 16, and it's negative, so negative 4. I'd like you to try these next two and then check your answers. 70 is between 64 and 81. So that's really between 8 and 9. And then the square root of 18 is really between the square root of 16 and the square root of 25. So really between 4 and 5. Alright, let's continue on. Here's a problem. It says the top of a folding table is a square, okay, that shape might be important, whose area is 221 square inches. Approximate the side length of the tabletop to the nearest inch. I made a mistake here. This should be 121 square inches. So if this is a square, the area is 121. We know the area of a square is just base times height. Well, if it's a square, we know those have to be the same, so it's really like x times x would be our area. Going even further, we know like 3 times 3 is 3 squared, so that's really x times x, which is x squared in this situation. But instead of just writing the word area, we know our area is 121. So base times height equals our area. But we want to know what x is. So we learned back here that the opposite of a square is the square root. So we're going to take the square root on both sides to get our answer and leave us with just x. Square root of 121 is 11. So that's just one side that we figured out. We found the length of one side of the table. And 11 is a rational number because it was a nice number. It made sense. It didn't come out as a decimal. Couple review problems down here. 9 squared, or 9 times 9, is really 81. 5 squared, or 5 times 5, is 25. 7 squared, 7 times 7 is 49. And last, 3 squared, 3 times 3 is 9. Now we're going to get on to a little bit of exponents, or not exponents, opposites. This is something that I just have to teach you. Most of you know this already. Well, if a is 3/4, then what's negative a? Well, negative a would just be negative 3/4, or the opposite of a is negative 3/4. Same thing here. If a equals negative 2.5, and we want the opposite of a, well, the opposite of negative 2.5, those two negatives just make a positive. So it's positive 2.5. Another thing that hopefully you learned last year was absolute value. The absolute value of numbers. Absolute value is really the distance from 0 on a number line, and it's always positive. I like to think of our absolute value as a shower. Anything that goes in our shower has to come out clean or positive. But if there's a negative outside that didn't go in the shower, that would be included on your answer. So this problem that they're giving us, A is -7, it's going in the shower. Anything that goes in the shower dirty, negative would be a dirty number, comes out clean or positive. Same thing, 15 goes in the shower, absolute value of 15 is just a positive 15. If there was a negative out there, then your answer would be a negative. But this one didn't have that. Down here, we're going to find negative A and absolute value of A. So if A is -5/6, the opposite of A would be a positive 5/6 because this one was negative. And then the absolute value of -5/6 is just going to be a positive 5/6. It went in the shower dirty, came out clean. Same thing over here. First, the opposite of A. The opposite of 2.7 would be -2.7. The absolute value of 2.7 would be a positive 2.7. Moving right along, evaluate the expression when x equals -4. So we're going to plug that in for x right there. So starting, it just says 2 times, parentheses, there's a negative coming from there. And then x is also a -4, so be careful. We know those two negatives have to make a positive. So 2 times 4 is just 8. Same thing here, we're going to put inside our absolute value -4, plus the opposite of x, and x is a -4 again. Remember, this negative came from here, this one came from x. Two negatives there make a positive. -4 went in the shower dirty, comes out clean, or +4. So we have +4 plus +4 gives us a positive 8. Alright, a couple more evaluating expressions. Here we have -3 times the square root of x, and x is really 121, and then -7. Let's simplify the square root of 121. Hopefully you get to know this one. It's just 11. And then we're following the order of operations. We don't have any parentheses or exponents. We do have multiplication and division, though. Do it from left to right. This comes first. -3 times 11 is -33. And then we just have addition and subtraction left. These are all negatives, -33, and take away another -7. Same sign, add them up. There's really a total of -40. The next one, let's do the same thing. Here it says the square root of x, and x is 64, divided by 8, and then that minus coming right from the equation. And then y is a -2, so this is really -2 squared. Following our order of operations, let's simplify our exponents and our square roots at the same time here. The square root of 64 is really just 8, so we have 8 over 8. That minus is from right there. And then -2 two times is really -2 times -2, which makes a positive 4. This negative is still coming from that sign there. 8 over 8 is just 1. So we did our multiplication and division. And then add and subtract 1, take away 4. Well, there's going to be more negatives. It's a -3. Last couple of things here, talking about rational and irrational numbers again. Rational numbers. First, our integers and whole numbers are also rational numbers because they're nice, round, counting numbers. Whole numbers start at 0 and are just the positives, 0, 1, 2, 3, 4, 5, and so on. Our integers are the negatives and the positives. So counting by ones, these are our integers. The difference is whole numbers are just positive. Then, Our rational numbers also include fractions. I could owe someone 1/4 of a pizza. I could have 2 2/3, pieces of cake. Whatever you want to think about it, however you want to think about it, any fraction is okay. It's a nice number. Same with any decimal. I could owe someone $2.34. I could convert a decimal to a fraction. 1/2 is the same as 0.5. Those are both rational numbers. They make sense. They end or they repeat. Like 2 2/3 would really be 2.6 repeating. That's okay. So here's some vocabulary to explain the same information here. So here is our first number, which is our real numbers. All the numbers that we deal with in calculus. All of our numbers are real. We don't have fake numbers or imaginary numbers or anything like that. Then we have rational numbers. Rational numbers are whole numbers, so our counting numbers, plus all the numbers that can be written as fractions. They either terminate or repeat, and they're also our perfect squares. So let's look at that for a second. Any counting number, any fraction, because any fraction we can also convert to a decimal. So that means our decimals that terminate or end or repeat. So fractions, decimals, and our perfect squares, like the square root of 9 is really just 3. So most of our numbers are going to be rational. There are only a couple that are going to be irrational. Irrational numbers are numbers that do not end or repeat. These are also our non-perfect squares. So non-perfect squares are square root of like 11. It's not going to be a nice number if you plug that in your calculator. It's also not on our list of perfect squares, like 1 times 1 on our multiplication table, 2 times 2, 3 times 3, 4 times 4. Those are the numbers we're looking at. 11 is not one of those numbers. And then also with that, pi. If you have pi, that's something that goes on and on and on. It does not end and it does not repeat. Pi is about 3.14 ... Integers, these are our counting numbers, 0, our positive counting numbers, 0, and negative counting numbers. These are the ones you see on your number line. Negatives and positives. But then our whole numbers just start at 0 and only the positive counting numbers. So the whole are just 0, 1, 2, this direction. So see the difference there. So let's take a look at a couple problems. Tell whether each number is a real, rational, irrational, integer, or whole number. Then order the numbers from least to greatest. Well, I told you all numbers are real, so those are free points. There's no fake numbers. But then we need to look, are these numbers rational or irrational? The only time you're going to have an irrational number is if you have pi or a square root of a non-perfect square, like 11. So 5, that's okay. That's a fraction, a decimal, just a regular counting number. 0.6, there's a fraction or a decimal. Yep, that's okay. Here's a fraction. Good, that's rational. You could owe someone $2.02 cookies. Square root of 24, though. If we look back here, square root of 24 is not on our list. It's really between 16 and 25. So it's really between the square root of 16 and the square root of 25, which is really between 4 and 5. So that's not rational. That's a weird square root. That's irrational. Then we have our integers. These are our negative or positive counting numbers. So this is a number you'd see on your number line. Yep. 0.6, we don't see decimals, we don't see fractions, and we don't see weird square roots on our number line. So the only one of these that's a counting number by ones is 5. Our whole numbers start at 0 and are just the positive counting numbers. So 5 is also a counting number. None of these ones are counting numbers by ones. So putting these in order from least to greatest, our least is automatically the negative number. If we have more than one, you go with the biggest negative number. So negative 2 2/3. Then, really close to 0, we have 0.6. Then we have either a number between 4 and 5, somewhere in there, or exactly 5. Well, the number that's between 4 and 5 would be a little bit smaller, so that's really the square root of 24. And then our greatest would be 5. Let's do the same thing down here with this one. Again, they're all real. There's no fake numbers. Then rational or irrational. Anything with pi or a weird square root is irrational. Everything else is rational. So 0.73, that's a decimal or fraction. Good. Fraction, decimal, counting number, we're good. Oh, but here's pi. Pi must mean that's irrational. If we plug that in our calculator, it will go on and on and on. And then negative 1/4, that's a fraction. That's okay. Rational. Then we have our integers, negative or positive counting numbers. The only one of these that's a counting number is 23, counting by ones. And it is also a positive counting number. 0 or positive, it's also a whole number. So from least to greatest, our only negative number is negative 1/4. Then we have 23, we have 0.73, and pi over 16. Well, I don't know what pi over 16 is, but I know pi is really close to 3.14. So you could just plug this in your calculator, or I know it's really close to 4 over 16, and that simplifies to 1/4 if you divide by 4. 1/4 is the same as 0.25. Well, since 3.14 is a little bit less than 4, I know it's a little bit less than 0.25, which is also less than 0.73. If that was a little bit difficult to follow, I completely understand. I just used some approximations because I know 3.14 is close to 4. 4/16, if we divide by 4, is the same as 1/4. And then 1/4 as a decimal is 0.25. Well, 0.25 is very much smaller than 0.73, so I know that one comes next, and then 0.73. Something's going on there with my smartboard. And then our greatest number would be 23. Alright, let's continue on. We got a couple more. We're going to do just the bottom one on this one, because they're all negatives. It'll be a little bit trickier. So skip this one. If you want to do it on your own, you can. These are all real numbers, but rational or irrational. Our only irrational numbers would be pi and weird square roots. So this is a fraction, that's okay. Here's a decimal, that's okay. Here's a counting number, that's okay. Here's another decimal, that's okay. So we don't have any irrational numbers. Our integers, the ones we'd see on our number line, negative, positive, or 0. Well, here's a fraction. That's not a nice, it's not going to be a nice whole number counting by ones. Same, here's a decimal. Nope. The only integer is negative 1. And then do we have any positive counting numbers? Well, you guys, they're all negative, so there aren't any positive numbers. So let's look. If I simplify this, or multiply it by 2, really, wouldn't that give me negative 6 over 10? 6 over 10 is 6/10, or negative 0.6. You could plug that in your calculator as well. So if we were looking at our number line, here's 0, here's negative 1. Well, negative 3/5, here's 1/2 in the middle here. Oops, I'll actually write that as 0.5 because we actually have that number right here. Negative 0.5. Negative 1's over here. Negative 0.4 is a little bit less than, a little bit greater towards the positives than negative 0.5. And then 0.6 would be a little bit further negative than negative 0.5. So if we go from least to greatest, our least are close to 0, close to the negatives, would be negative 1. Then our next biggest negative number, negative 0.6, then negative 0.5, and then negative 0.4. Instead of 0.6, if you put negative 3/5, that would be a better answer. Our last problem here, all of these are square roots. Let's evaluate them still. Well, I know the square root of 100 is 10. I know negative square root of 81. Square root of 81 is really just 9 because 9 times 9 is 81. But 24, it's really close to the square root of 25. So it's a little bit less. So our next one below that would be square root of 16, so because it's really between 4 and 5. So let's look. Are these real? Well, they're all real. There's no fake numbers. Rational and irrational. There's no pi here. So the only ones that would be irrational would be our weird fraction, or weird square roots that are not normal, not nice numbers like square root of 24. But square root of 100 is just 10, that's okay, rational. Same with 81. Integers, these are ones on our number line, negative or positive. Well, 10 and negative 9 would both be on our number line, but some decimal between 4 and 5 would not. And then our whole numbers, counting positives by ones, just number 10. So our least is the negative square root of 81. Then a number between 4 and 5 would be smaller than 10, so square root of 24. And last, square root of 100. Alright, you do have a homework assignment, so make sure you try your best and show your work.